Hey guys, today we're going to be focusing on sound and hearing and essentially how the your cochlea works and how it works with your outer ear, inner ear, or external middle ear and inner ear. How sound waves generate action potentials from start to finish essentially. So first thing we need to talk about is hertz, and what these are frequencies, number of peaks in a wave that pass a certain point per second, and audible range is going to be from 20 hertz to 20,000 hertz is what we can hear. And amplitude, so we talked about points or peaks of a wave passing per second, but those peaks can be stretched up and down such that their amplitude is higher, and that's what will determine how loud the sound is. So you can have a certain pitch louder or softer depending on its amplitude. And we measure amplitude in terms of decibels, and each time you go up 10 decibels, that's a logarithmic function, such that if you go up 10, you're going to go up 10 times the amount of volume. So something to keep in mind there. So let's look at kind of the anatomy of your ears, your outer ear, your middle ear, and your inner ear. Some of the structures that work with that. We have your auricle, which is what is kind of like shuttles all the sound waves. It gathers it all like a funnel. Then you have your what was it called? Dang it. Well, it'll come back to me. Anyways, it's a canal, your auditory canal, pretty sure, and then that will attach to a tympanic membrane, and this tympanic membrane will then attach to it's the border between your outer ear and your middle ear, and within the middle ear you have ossicles, and these ossicles are little tiny bones that amplify the sound or amplify the vibrations that come from this tympanic membrane, which is vibrating with these frequencies. So the malleus is your first one, then your incus, and then your stapes, and they kind of hinge a little bit such that they amplify the frequency that they're receiving from the tympanic membrane. So the stapes will attach to something called an oval window, and the oval window is kind of the border between your middle ear and your inner ear and the cochlea. And so the oval window is smaller than the tympanic membrane, but because it's been amplified by the middle ear, the oval window is gonna vibrate, much like the tympanic membrane. So let's look at kind of the anatomy of the cochlea. It's kind of a spiral figure. You'll have the cochlear duct, which will house your organ of Corti. Then you have a basilar membrane, which is responsible for detecting different frequencies. Within this spiral, you have endolymph, your cross section of the cochlea right here. You'll have endolymph inside, which will be a high concentration of potassium, which we'll discuss later. Perilymph is on the outside of that. So there's several different chambers within the cochlea, and what you need to know is once you vibrate the oval window, you're pushing and pulling on that fluid on perilymph in the ear or in the cochlea, right? You're moving that fluid, and that fluid's going back and forth, and once you turn the corner and come all the way to the other end of the cochlea, you hit the round window, which is gonna push out when the oval window goes in, and it's gonna pull in when the oval window goes out. So you're just oscillating between those two membranes and those windows. Yeah, so you're pushing on it, perilymph moves, but that's gonna create a certain frequency which we can detect. So what's gonna what is gonna detect those different frequencies of the fluid and how the fluid is moving is gonna be your basilar membrane, and that's detecting those different frequencies of the fluid movement, the oscillations of the fluid. And sitting on top of that basilar membrane is called the organ of Corti, and that's, you can see it here, kind of has all your hair fibers and such, your hair cells and nerve fibers, and that's going to convert these mechanical vibrations of the fluid to action potentials because it sits right on top of the basilar membrane. Let's look at the makeup of the basilar membrane. It's kind of like a xylophone where you start with small little keys and then you move up to bigger ones. The reason that's set up is because the smaller keys are going to be more sensitive to higher frequencies. And then as you move down the basilar membrane, or the xylophone, so to speak, you'll have bigger keys which are more sensitive to lower frequencies. And that spirals with the cochlea. But yeah, it's found here in this cross section if we look here. So let's look at this cross section. You have your basilar membrane, which will detect different frequencies, and you have your tectorial membrane, which is kind of like a shelf that sits over the top of your hair cells. So in total, you'll have 4 hair cells, 3 of which will attach to your tectorial membrane. And the reason it does that is so that when the basilar membrane moves, it's going to shift those hair cells such that the hair cells are then going to move and open gated channels. Another reaction occurs when those start to move is once these hair cells start moving, a protein called Prestin will tighten up the basilar membrane, which will amplify the sensitivity to that certain frequency. And it'll also kind of pump down this tectorial membrane because we tighten the basilar membrane, we've shortened the distance, so now it's more sensitive. And that will cause a lot of this fluid to flow in and out because we're pumping this tectorial membrane, and that will hit the inner hair fiber or inner hair cell, and that will also cause potassium to flow into the inner hair cell as well. So between your outer hair cells and your inner hair cells, you can have action potentials going through them, simply because we're depolarizing it with potassium. So what's going to happen is we're going to pull on these hair cells and once they have tension on them and they move, they're going to allow potassium in. That's going to depolarize the hair cells. When you depolarize it, you allow calcium to move, or you allow calcium in, much like other neuron or graded potentials or action potentials. You allow calcium in, that allows neurotransmitters to be released. In this case, we're releasing glutamate, which will be an excitatory postsynaptic stimulus. And so we've just released glutamate into the synaptic cleft, and that will send action potentials from your hair cells, inner and outer, all the way to the brain. And that's how we detect sound. I think I forgot to mention, or just to reiterate, with the basilar membrane, it only detects certain frequencies at certain locations on it. And so as you go from higher frequency to lower frequency, you're moving down this basilar membrane, and you'll be sensitive to higher and lower frequencies depending on what's being played or what you hear. So that's how sound and hearing works, and how we can generate action potentials due to sound.